Hello, everyone. Thanks for joining our presentation on an investigation of reservoir rock property measurement methods for sandstone and shale samples. My name is Eric.
And my name is Sue. To briefly summarize the study done this year, 118 sandstone and 10 rock and shale core samples were used to measure the porosity and permeability using a variety of core analysis methods found in the petroleum industry. In the past, many of the low permeability reservoirs were sandstone, but significant quantities of oil and gas from low permeability unconventional shale reservoirs have been developed in recent years in the United States. To introduce our study, it is important to define permeability and porosity, especially for those not familiar with these rock properties. The capacity of a rock to contain fluids is quantified by porosity, and the movement of the fluid throughout the pore throats is known as permeability. Conventional sandstone and unconventional Bakken shale were tested under stress that was representative of reservoir conditions. The standard density of sandstone of 2.65 grams per centimeters cubed was used for reference in case the measurements became inconsistent, but shale does not have the consistent density due to its composition and biogenic material. This figure shows the microscopic structure of shale on the left side, which is much smaller than the sandstone shown on the right side.
The foundation for our experiments were derived from an application of Boyle's and Darcy's law. For example, a modified version of Boyle's law that uses multiple known volumes was utilized by the CMS 300 and the ultrapycnometer to find the pore volume of a core sample. Any measurements defining permeability would use Darcy's law since flow is being observed. So this law was the foundation of using the Ruska permeometer and CMS 300 again. Finally, Archie's equation was used for resistivity analysis with a variation of that equation shown. Additionally, we wanted to develop a better understanding of the impacts that a high net stress could have on a sample reservoir's properties. The CMS 300 was used for this again, since samples could be placed under a high confining pressure. These four graphs show how each porosity measurement method compared to our most trusted tool, the CMS 300. Ideally, all data points would be along the dividing line, meaning that both methods measured the same porosity. If the points are more prevalent on one side, however, then that method could be associated with a larger error. The CMS versus estimated porosity in the top left showed a moderate spread. This was useful since the prediction of porosity values gave us a better working understanding of the nature of our samples. Next is CMS 300 versus pycnometer in the top right appears to have the closest spread centered about the trend line, showing a general agreement of the porosity measurements. However, fluid saturation shows a spread of values along the x-axis that was not centered about the ideal line. Resistivity analysis was excluded from this visualization since measured values were far from the ideal line and associated with a significant error. So for our sandstone core samples placed under a high net stress called overburden, we saw a trend of the sample under high confining pressure is that porosity and permeability will decrease since it's kind of being squeezed together. However, a few samples showed a small increase in permeability at different confining pressures.
Increasing the pressure of the CMS 300 would tend to decrease the porosity and permeability of the core sample due to the constraint of the pore spaces, but this trend was limited for the Bakken shale core samples. As observed in the graphs on the left side, shale 2, shale 3, and shale 6 had a decrease in porosity, and this was because the core samples were very tight with increasing pressure. Some of the shale samples slightly increased their porosity with increasing pressure, such as shale 1, shale 4, shale 5, and shale 7. One shale sample decreased significantly with increasing pressure, such as shale 10, due to the possible microfractures in the rock, and some of them remain consistent, such as shale 8 and shale 9. The plots on the right side for permeability versus net stress, it was possible to observe the decreasing trend of permeability as pressure increased for every shale core sample.
For conclusions, an important consideration is that while porosity is a scalar attribute, permeability could be considered a vector, meaning that measurements of this property are path dependent, which may explain an increase in permeability in combination with microfractures like Siew had described. From our results, we can conclude that permeability is sensitive to stress, and while porosity is reduced by high pressure, it is less sensitive to stress than permeability. The CMS and pycnometer are our most accurate tools. A potential reason for this is that these tools use gas, while the resistivity and fluid saturation techniques have to use a liquid brine solution. The gases used are nonpolar and don't interact with the surface of pore walls in the same way a brine solution might.
And for future research, it is recommended to use the CMS 300 and the pycnometer equipment due to their accuracy values. but the estimated values using the core basic data is a good start for preliminary understanding of the core samples. And the methods used in this study could be applied to other core samples, such as limestone and dolomite.
These are our materials we refer to in our research. We both want to thank you and encourage those of you with questions to leave them in the thread below.
Thanks.
Thanks.